Okay, problem number 19 from section 8.2. Now, what I'm going to do, I want to take this on a couple of different levels. Let's start by looking at this graphically and see if, when we look at it graphically, whether we get any insight about where we think we're going with this problem. All right, so let me cover this up, move this over here for a second, and let's go ahead and put into our grapher cosecant, which is 1 divided by sine of x. Move over here, please. All right. Minus cotangent, which is 1 over tangent of x. And then we're going to add on to that cosine. And I'll do zoom 7, although since we're trying to investigate what's going on near 0, that should be sufficient. Okay, what do we got there? What do we think is happening as x approaches 0 from the right-hand side? Looks to me like it's looking to be about 1. So far, so good? All right. So, looks like it's about 1. And let's see what analytically we can do with this problem and see if we can confirm that as well. Now, when I try to plug in 0 into cosecant, if I remember correctly, the graph of cosecant, it's actually undefined at 0 and has behavior like this and like that. So it looks like from the positive sign, cosecant x goes to infinity. When I think about cotangent, so this is y equal cosecant x. When I think about cotangent, I believe it's also undefined at 0 and has behavior that looks kind of like this. Well, that's terrible. That on every multiple of pi, every even multiple of pi, it's undefined. All right? So I've got a couple of things, but this part here looks like infinity minus infinity. Everyone okay with that idea? And we have declared infinity minus infinity to be indeterminate. Because infinity comes in different sizes, you know, and because we don't know whether it's a big infinity minus a small infinity, maybe it's a negative number, positive number. Maybe it's a little infinity minus a big infinity, and so it's a negative number. Maybe these two infinities are about the same size, and they cancel each other out. Since infinities come in different sizes, we are indeterminate what this infinity minus infinity looks like. So let's see if we can attack it using L'Hopital's rule, and hopefully something will come of it. Oh, the calculator is still, there we go. All right, so L'Hopital's rule. L'Hopital needs something in the form 0 over 0 or infinity over infinity to be used, and we don't have that yet. But maybe we can massage it and make it happen. Evan, you look like you wanted to say something, and I was ignoring you.
Well, with the cosine right after the infinity minus infinity form, what do we do to that? Because as that specific part of the expression approaches 0, it approaches 1.
Infinity minus infinity plus 1 is still
right,
minus infinity.
right. So this cosine thing, since nothing's going on special with that, and because one of the rules that we talked about yesterday was that I could simply rewrite this as the limit as x approaches 0 from the positive side of cosecant x minus cotangent x plus the limit as x approaches 0 from the positive sign of cosine x. I have the ability to break those limits down into separate sums. And we can see that's going to 1. We can set it aside. I'm not too worried about it. All right, let's get back to how we're going to attack this. I'm going to rewrite cosecant as its definition. 1 over sine of x. I'm going to write cotangent as its definition, which is cosine over sine of x. And I'll just put a plus cosine in there for good measure. And now, do you see what I'm going to do next? Common denominator. Let's attack it with the common denominator. So my common denominator is sine. So I get 1 minus cosine plus, you know what? I think I'm just going to say that plus 1 got handled. I think I'm just going to focus on, oh, I hate doing this. I'm going to do it anyway. I'm going to say I know that the cosine goes to 1, and I'm going to put a 1 in front. And then I'll do my 1 minus cosine over sine. I'll just try it that way. Yeah?
I don't really understand what we would like that you're just like the 1 based on.
Well, are you okay? Are you okay with this portion of the rewrite? All right. Do I know what happens as x approaches 0 to what happens to cosine as it approaches 0? It goes to 1. So what I'm going to say is, oh, this whole thing is a great big honkin' 1. And since it simplifies my work, why don't I just set that aside and have that 1 show up there, and then I'll figure out what the limit of the rest of it is. This is Todd. Yeah? Mm-hmm. Okay. All right. Fine. Mr. Malonis, you're requested down at the office. All right. So Nicole, are you okay with that manipulation? All right. So let's focus on this and find out, is this indeterminate in a form that we like? When I try to plug in the zeros, cosine's going to go to 1. 1 minus 1 goes to 0. I got a 0 on top. What about sine? It goes to 0. I've got an indeterminate. I have a ratio that's indeterminate in the form 0 over 0. And with that, I'm willing to apply L'Hopital's rule. And that is the derivative of the top is going to be negative sine. The derivative on the bottom oh wait, the derivative of cosine is negative sine, but I got another negative, so that's positive. And then on the bottom, cosine. Now, is that indeterminate? Sine goes to 0, but cosine goes to 1. No, that's not indeterminate. It's 0. And there's our answer, 1. And what do we say? Well, matched graphically what we thought we were going to get. Good, Evan? Yes?
Can you please go over number 11?
Number 11?